Welcome to my presentation about our paper, Visual Descriptor Extraction from Patent Figure Captions, a case study of data efficiency between BioLSTM and Transformer. The number of patents in the United States has been steadily increasing in recent years. Particularly in 2020, there is a large volume of patents along with a large number of patent figures. This brings challenges to the patent figure processing and management, so we need to make improvements by finding better ways for analyzing and understanding technical drawings. In this paper, we focus on extracting textual descriptors for technical drawings and design patents. They can be used to build search systems to help patent examiners to search for similar designs. More importantly, they can be used to build a large-scale dataset to train computer vision models. As shown in the picture below, the benchmark dataset ImageNet is annotated manually, but we use an NLP method to annotate patent drawings. In contrast, our annotation is automatic. There is an example for patent figures. In a patent figure, there is a technical drawing and a figure label. In each patent, we also have a patent document in XML format, which contains figure captions. We can use the corresponding figure caption to extract object and aspect names for each figure. We use named entity recognition to obtain the objects and aspects from figure captions. However, we cannot directly apply pre-trained NER models since they only focus on specific types of tags, such as organizations and person names. So we have to build our own model. First of all, we have to build a ground truth corpus, and this is done manually. We randomly selected 3,300 figure captions in the 2020 dataset from USPTO patent database. And then they are annotated manually. The figure below is an example of annotation. We have to specify aspect and object in a figure caption. In practice, we annotate each token in the sentence with a tag. We follow the BIO schema with 5 tags. Here, B means beginning, I means the inside, O means outside. The ground truth corpus is split into training, testing, and validation datasets. The training dataset contains 2,700 figure captions. After we have obtained the ground truth corpus, we use it to train our model. We compared 2 state-of-the-art architectures by LSTM CIF and the transformer. In the BioLSTM CIF architecture, input embedding is actually pre-trained language model, such as BERT. We compared 7 different embedding models. Input embedding convert each token in a sentence into embedding vectors, and those vectors are input into the BioLSTM layer. And then this layer outputs the scores of possible tags for each token and input them into CIF layer. This layer learns the joint relationship between tags and then refines the probability scores for each token. Finally, we pick the tags with highest probability and form the best tag sequence. This is what we want. We also build our model with the transformer architecture. It encodes the contextual information and outputs the probability scores for each token. There are some results for the BioLSTM CIF architecture. The F1 scores for all entities is above 90% for all embedding models. The embedding models trained by a transformer architecture such as BERT, Albert, the top 5 ones, has better performance than the others. The 2 embedded models on the bottom. Among them, the Dilbert gives the best performance with F1 score 96.6%. We also compared the results for both by LSTM CIF architecture and the transformer architecture. For each embedding model by LSTM CIF gives better performance, higher F1 scores than transformer architecture. The biggest difference is given when we use Roberta and OpenAI as embedding model. So the best model here is Dilbert by LSTM CIF. This is used to train the model and used for subsequent tasks. We have some observations about data efficiency when we do the training. First of all, we vary the training data size from 500 to 2,700. And we can see from the diagram, F1 scores of the transformer models increases as the training data size increases. But the curves for transformer models are consistently below the curves of by LSTM CIF models. And by LSTM CIF model has consistently good performance above 90%. They can generate good results with a small training dataset. This shows the good data efficiency of by LSTM CIF model. As shown in a previous slide, the training data contains 2,700 figures. And there are 557 distinct object names and 346 distinct aspect names. This is used to train the Dilbert by LSTM CIF model, and then it's used to annotate the enabled corpus. This corpus contains 66,417 figures, and we extracted 6,405 distinct object names and 2,210 distinct aspect names. Only a small portion of that are in the training data. In other words, the majority of objects and aspects extracted are new. This shows the good ability of our model to generalize. Finally, here comes the conclusion part. In this paper, we proposed an effective visual description extractor using the by LSTM CIF sequence tagging model, achieved an overall F1 score 96.6%. We compiled a dataset containing 3,300 captions with human annotated visual descriptors. This is publicly available and it can be used to train NLP models. We automatically extracted object and aspect descriptors of 66,417 pattern figures using the trained by LSTM CIF model. This dataset is also publicly available. We performed a data efficiency study and find that transformer exhibits a much steeper data efficiency curve. But the performance is worse than by LSTM CIF in all the scenarios we have examined. This is the conclusion. It summarizes the main idea of our paper and our contributions. Thank you for listening to my presentation.